All right, so the next part of the graded titration practice, I'm actually going to do part C. Remember, part B is evaluated or calculated just the same way. All you need to do is plug in different numbers. So C was 15 milliliters of the titrant, which is 10th molar sodium, or 10th molar hydrochloric acid, or just 10th molar H3O plus hydronium. So during the titration, probably the first thing you need to make sure that you're clear on is what the titration reaction actually is. And in this case, it's going to be our weak base, trimethylamine, which is abbreviating as TMA. So this is a weak base. It's going to react with the strongest available acid, which now, since we have begun the titration, is just hydronium, H3O plus. And since one of those pair is a strong acid, the hydronium, you can assume this reaction goes to completion. So there'll be a transfer of the proton from the acid to the base, which will result in the protonated trimethylamine, HTMA plus, and water. So now it's useful to actually figure out how much of your trimethylamine has been reacted by the addition of the acid. So the first thing you need to do is to figure out the amounts of both compounds at this point. So for the trimethylamine, now remember, concentration times volume gives you an amount, and you had 0.015, this is for the HCl, sorry, the hydronium. You have added 0.015 liters of it, and it has a concentration of 0.1 moles per liter, so that's going to give us 1.5 times 10 to the negative 3 moles of hydronium. The trimethylamine, you were told that you had 20 milliliters or 0.02 liters of the stuff with a concentration of also a 10th mole per liter. So that's going to correspond to an amount of 2 times 10 to the negative 3 moles, or 2 millimoles. So now we're going to build not an ice table, but what I like to call a reaction table. And I'm going to start by expressing things in amount, in moles. So we initially have 2 times 10 to the negative 3 moles of the trimethylamine, and 1.5 times 10 to the negative moles of hydronium. We're going to say no trimethylammonium, and the water is not really going to matter. So this is the hypothetical case after they've mixed, but before actually reacting. So looking at these numbers, everything reacts 1 to 1. This is still not enough hydronium to react with all of the trimethylammonium. So you can assume that we're going to react all of that away. It's going to be the limiting reactant. So we expect to lose that whole 1.5 millimoles of hydronium. And we'll also lose 1.5 millimoles of the trimethylammonium, which will give us 1.5 times 10 to the negative 3, or 1.5 millimoles of the trimethylammonium as well. So, after the reaction, we can expect to have millimole of the trimethylammonium left. We're not at the equivalence point yet, so we'll have no hydronium. And (1.5 millimoles of the trimethylammonium. Now, you might want to determine the concentration of the trimethylammonium and the trimethylamine once all this is said and done. And that's pretty simple. What you need to be aware of, though, is that the volume is no longer 20 milliliters. It's not 15 milliliters. It's 20 milliliters plus 15 milliliters. Or 35 milliliters. So if you divide those amounts by the new volume of 0.35 liters, this is now the concentration of the remaining trimethylamine is 0.02 molar, and the concentration of the trimethylammonium is now 0.06 molar. And our concentration of hydronium is pretty much 0. So since we have significant concentrations of both this weak base and its conjugate acid, we can really quickly calculate the pH just using the Henderson-Hasselbalch equation, because this is in the buffer region. So the Henderson-Hasselbalch equation just relates the pH at a particular point to the pKa of the acid and the base 10 log of the ratio of the concentration of the conjugate acid and its base. So the one thing that you don't know just yet is what the Ka of the trimethylammonium is. But you can figure it out because you know Kw and you know you were given Kb. So the Ka of trimethylammonium is simply Kw divided by the given Kb, and that ends up being about 1.92 times 10 to the minus 11th. And everything else you have here. So this is going to be the pKa is just the negative base 10 log of the Ka. Plus log, and then just the ratio of the concentrations of the base. Now, keep in mind this is usually written as A minus and HA, but remember this is, in our case, the base is neutral, and it has a concentration of 5, oops, no it doesn't. It has a concentration of 0.02 molar. The acid is the trimethylammonium. It has a concentration of 0.06 molar. And if you plug all those numbers through, you get a pH of 10.24. Which is a reasonable number. We're still in a basic regime, but again, we're not done titrating the weak base, so that's to be expected. And next up, we'll get the pH at the equivalence point.